morning, all the participants. We are here to attend the lab session 4 of day 6. So now I would like to invite Dr. Bhaskar Avadia from Manipal Academy of Higher Education, Mahe, Manipal University, Karnataka. So I welcome Bhaskar Avadia sir to continue his lab session.
Hello, good morning to all the participants. And first of all, I would like to thank Bansal Institute of Science and Technology for providing me the opportunity to present my things in front of you. So this is the continuation of lab session 4, I think. Day before yesterday, I have given one lab session. So this is the continuation. In that session, we basically looked upon the isolated ferroelectric capacitor and the capacitance enhancement and the passive voltage amplification. Now in today's session, it will be a short and crisp session. I would discuss about temperature analysis of heterostructure. So for that, I'll first go to board, I'll explain a little, then we'll move on to the tool and we'll see a few simulations. Okay, so now as we all know, the ferroelectrics is governed by an equation which is known as LK equation. Landau-Khalatnikov equation. And this equation says Vf equals to alpha QF plus beta QF to the power of 3. There is one more term called gamma, but because as we are considering the second order transition material, the ferroelectrics material can be classified into two types: first order transition material and second order transition material. So in second order transition material, we can neglect the value of gamma. And we are considering here second order transition material because we are considering lead zirconium titanate. So I have not considered the value of gamma over here. So I have taken gamma as 0. So this is the equation, Vf equals to alpha QF plus beta QF to the power of 3. Now, where Vf is the voltage across the ferroelectric and QF is the charge across ferroelectric. And alpha and beta, which I have been telling from the day 1, it's the anisotropy constants. So here alpha and beta are anisotropy constants. And I think in the earlier session, I have already told how to get the values of alpha and beta with the help of corrosive field and the remanent polarization. Now, as we all know, Q equals to CV. So I can write C equals to dQ by Q. So what I am doing here, I am differentiating this particular equation. I am differentiating with respect to QF. So what can I write? dVF by dQF equals to alpha plus 3 beta QF square. I can write dVF upon dQF equals to alpha plus 3 beta QF square. Now, this is inverse of capacitance. This is 1 upon Cf. So I can write 1 upon Cf equals to alpha plus 3 beta QF square. Further, if I have to write Cf, I can write Cf equals to 1 upon alpha plus 3 beta QF square. Now further, I can approximate this value of Cf. I can approximate the value of Cf equals to 1 upon alpha. So if this charge has a small value, QF square will be further small. So I can neglect this particular term and I can say CF is approximately equals to 1 upon alpha. Now alpha is an anisotropic constant. I told you how we can calculate using corrosive field and the remanent polarization, but it has one more relation because that particular alpha is dependent upon the temperature. So I can write alpha equals to alpha naught into T minus, where alpha naught is the material constant. It is a material dependent parameter. It varies different for different material. T is the temperature and T naught is the Curie temperature. So one thing to note over here, there are two temperatures, Curie temperature and Curie-Weiss temperature. So for second order transition material, Curie-Weiss temperature and Curie temperature both are same. Tc equals to T naught. And for first order transition material, the Tc and T naught doesn't coincide with each other. But anyways, we are considering here only the second order transition material. So I can say alpha naught is the positive material constant. It has a positive value, and T naught is the Curie temperature. Now what I'll do, I'll put the value of alpha into CF. So this I can write CF equals to 1 upon alpha naught T minus T naught. So this is the expression for ferroelectric capacitance, and it is a function of temperature. So what happens? Till the Curie temperature, my material behaves as a ferroelectric, and once the Curie temperature is reached, the material starts behaving as a paraelectric material. So till Curie temperature, it is behaving as a ferroelectric, and after the Curie temperature, it is behaving as a paraelectric material. So this expression we'll be doing in the tool also. So first what I'm thinking is I'll explain everything and then I'll go to the tool. So we can note this equation somewhere so that I'll note down this here. CF equals to 1 upon alpha naught T minus. This is one of the important equation which I'll be discussing when I'm telling in the tool. So I have noted it separately. Now this was about the isolated ferroelectric capacitor, how the ferroelectric capacitor changes with temperature. Now let's see with respect to the heterostructure. So in heterostructure, what we are doing? There is a ferroelectric material and below that we have used a dielectric material. So it's like two capacitance are in series to each other. And if two capacitance are in series to each other, the equivalent capacitance will be C1 C2 upon C1 plus C2. Or I can write 1 upon C equivalent equals to 1 upon C ferroelectric plus 1 upon C dielectric. So let me just see what happens. So first of all, I'll erase this thing. Now we are discussing the case of FEDE heterostructure. Now in FEDE heterostructure, both the ferroelectric and dielectric capacitance are in series to each other. So what can I write? I can write 1 upon C equivalent equals to 1 upon CFE plus 1 upon CDE. Now we have because this is F, we can write here FE also, both are same. So this is CFE. We already know the value of CFE. So can I write 1 upon C equivalent equals to alpha naught T minus T naught plus 1 upon CDE. I can write like this. So 1 upon C equivalent equals to alpha naught into T minus T naught plus 1 upon CDE. Now what I'll do, I'll open this bracket and I'll write 1 upon C equivalent equals to alpha naught T minus alpha naught T naught plus 1 upon CDE. Now next case what I'm going to do is I'll take alpha naught common. So if I take alpha naught common, this becomes T minus T naught plus alpha naught, no, this will be 1 upon alpha naught CDE. So because this, when this goes inside, this becomes alpha naught T naught, and this becomes 1 upon CD. So this is okay. Now further, I can write 1 upon C equivalent equals to alpha naught, and I can write T minus T naught minus 1 upon alpha naught CDE. And C equivalent can be written as 1 upon alpha naught T minus T naught upon T naught minus 1 upon alpha naught CDE. Now, if we try to compare this with that, so this is my material dependent parameter alpha naught, and this is a new Curie temperature. This is nothing but a new Curie temperature. New Curie temperature. So that temperature was for ferroelectrics, and this temperature is for FED heterostructure. So what is new Curie temperature? T naught minus 1 upon alpha naught CDE. Now interesting to note over here that the new Curie temperature is less as compared to the isolated ferroelectric capacitor. We can make a note over here that the new Curie temperature, let's say T naught dash would be T naught minus 1 upon alpha naught CDE. So this expression also we need to note. C equivalent equals to 1 upon alpha naught T minus T naught minus 1 upon alpha naught CDE, and this is the new Curie temperature. So at present I am explaining everything, then I'll show everything in the tool. Now there is one more parameter which is voltage amplification. We need to see the voltage amplification with respect to the temperature. Now as we all know that both the capacitance are in series to each other. Now let's calculate how the voltage amplification is going to get affected if we vary the temperature. So let me just erase all the things. Now, so I have a heterostructure like this. This is my ferroelectric material Fe. this is my dielectric material DE, this is my metal METAL metal, and this is my metal. So I can generalize this with two capacitance. So here what is happening, I am applying a source Vs, I am applying Vs, and voltage drop across ferroelectric is VFE and voltage drop across dielectric is VDE. So here, let me draw it once again. So here there is a ferroelectric capacitance, dielectric capacitance, and we have Vs. So this is CFE and this is CDE, and this voltage drop across dielectric is VDE, and this is VFE. Now, as I told in the earlier talks or the earlier sessions, that there is a provision of voltage amplification. And voltage amplification means what? The voltage drop across the dielectric capacitance will be more than the supply. So if I apply a normal KVL over here, can I write VDE equals to potential divider mass I am going to apply Vs into 1 upon S CDE upon 1 upon S CFE upon 1 S CDE. So I can further solve it as VDE equals to Vs. So this S is the frequency, not to be confused with S. Vs is the supply voltage and S is the frequency over here. So there should not be any confusion. So I'll take LCM over here. So this becomes SCFE CDE, and this would be CDE plus CFE. Now if we solve this, VDE by Vs equals to 1 upon SCDE into SCFE CDE upon CDE plus CFE. Now this S and H gets cancelled and CDE and CDE gets cancelled. So what is remaining over here? VDE or VD upon Vs equals to CFE upon CFE plus CDE. Now if I take the this CFE value we have already known to me, so this would be 1 upon alpha naught T minus T naught upon CFE is what? 1 upon alpha naught T minus T naught plus CDE. So this is the voltage amplification. So this is voltage amplification, and we have obtained a relationship of voltage amplification in terms of temperature. So this was one equation, number 1. This is number 2, and this is number 3. I can write VD by Vs equals to 1 upon alpha naught T minus T naught upon 1 upon alpha naught T minus T naught plus Cp. So this is the ferroelectric capacitance with respect to temperature. The second equation is equivalent capacitance with respect to temperature, and this is the voltage amplification with respect to temperature. Now, the common thing which we have to note is alpha naught. Alpha naught has some value for PZT, because here I am considering the material as PZT, which is lead zirconium titanate. So alpha naught has some value and T naught has some value that I'll show in the tool, and then afterwards I'll write here. So this was about the theory. This was about the theory. Now let's go to the tool and just see how the response will look like. So I'm going to the tool. So this is the same tool, Desmos. So I have not logged in, so I log in through my mail ID. So this would be now. This is my graph. Now this is capacitance versus temperature. This is capacitance versus temperature. Now here I have written CFE equals to 1 upon alpha naught T minus T naught. Now I just told that for lead zirconium titanate there is a certain value of alpha naught. Alpha naught we have got from an literature, and I'm writing alpha naught equals to 1.5531 into 10 to the power 12, and the temperature is 684. Now if you can see, this is CFE. CFE is on the y-axis and temperature is on x-axis. So we can see there is a, just a second, we can see the capacitance increases in this phase. So this below this temperature, this is a ferroelectric phase over here, and this is a paraelectric phase over here. So at this particular temperature, the ferroelectric material is converted into paraelectric material. So till this temperature, your capacitance was increasing, and this is in ferroelectric phase. And now here the capacitance is decreasing, and now it is in paraelectric phase. So this was the graph number 1 for equation number 1, which I have derived over there. Now let's go to the graph number 2. This is the graph number 2. So again, I have plotted the graph for ferroelectric. So this graph is for ferroelectric. So up to 684, it is increasing, and it's falling after 684 temperature. This graph was for the ferroelectric. Now what has happened? Now I am considering the dielectric also. Now as I told when I was explaining in the board, heterostructure means there is a series combination of two capacitors. So equivalent capacitor will be C1 C2 upon C1 plus C2. So if you see, this is the C equivalent, and this is C1. C1 is ferroelectric, C2 is dielectric. C1 plus C2. C1 is ferroelectric, C2 is dielectric. And please note down here that dielectric capacitance, I have taken the material for dielectric capacitor. I have taken the material as silicon dioxide, SiO2, with a permittivity of 3.9. D separation between the plates will be 1 nanometer, or thickness of dielectric I have taken as 1 nanometer, and the area of the heterostructure is 45 nanometer cross 1 micrometer. So 45 nm cross 1 micrometer. So if you solve this, you will get 1.593 into 10 to the power minus 15 farads. Okay, so now just look this. This is the equivalent capacitance as a function of temperature. I have plotted over here. Now you can see this Curie temperature, which was 689 in my previous case, in heterostructure it is reduced. And this is what I was explaining in the board that time. What is the relation that I got? C equivalent equals to 1 upon alpha naught into T minus T naught minus 1 upon alpha naught CDE. So the new Curie temperature is less than what we obtained in our previous case. So here the Curie temperature was 684. Here the Curie temperature is somewhat less as compared to the previous case. So this is what I was trying to explain. Now this was about the temperature. Now let's look at how the temperature is, how the voltage amplification is going to get affected by our temperature variation. So for that I have graph number 3. Now this is the graph. Now just now I have derived an expression for voltage amplification Vd by Vs. Vd by Vs, what can I write? I have written 1 upon alpha naught t minus t naught upon 1 by alpha naught t minus t naught plus CDE. So this we are going to plot over here. So this is the amplification versus the temperature. If you see, we have plotted the amplification with respect to the temperature. And here you can see the amplification, because this amplification is more than 1. So here amplification is observed in the case of heterostructure. So this was about the temperature analysis of the heterostructure. So I have told the theory, how we are achieving that. I have told the theory, as well as I have plotted using the tool also. So if you guys have any queries, please feel free to ask. From the audience side, if questions are there, the questions are welcome. No questions? So I think the session which I took in the 3 days was interactive, and you guys have got some insight into ferroelectrics and the negative capacitance. So if you guys don't have any questions, so this is it for today and today's lab session. And thank you very much. Once again, I would like to thank Bansal Institute of Science and Technology for providing the opportunity to express my views and a little insight into ferroelectrics and dielectrics and the heterostructure as well as NCFET. Thank you so much. Thank you so much.
Thank you, Dr. Bhaskar Rawadiya, for giving such a great session. Now this is the end of this lab session. Thank you very much.